We've talked about the expansion of the universe. Now let's take it a step further and talk about the acceleration of the expansion. Here's the expansion history of the universe. As people recognized the universe was expanding, and they realized that when we look out in space, we look back at time, they started to do an experiment. They thought that as you looked further out in space, since dark matter, the stuff of the universe that goes against gravity, that's retarding the expansion of the universe, dark matter should decelerate the cosmic expansion. And so that means, looking back in time, they expected to see the Hubble law curve, that the expansion rate would either be constant or faster in the past, indicating that going forward in time, the cosmic expansion had decelerated due to the influence of dark matter. That's what gravity would lead you to expect. So it was a very clear expectation. It took a while for data to be good enough to do this experiment and actually look back in time more than a couple of million parsecs, which is a couple of billion light years. But this is what was seen. It was the opposite to what was expected. The objects that were found were fainter than they expected to be, and so it seemed that they were further away than they were supposed to be. And the inference of these observations was that the universe, looking back in time, was slower. In fact, the universe has been accelerating since 3 or 5 billion years ago. That's extraordinary. That means that the decelerating universe in the first 4, 5, 6 billion years of its existence has changed to an acceleration in the last few billion years. That was a total shock. This happened in 1995, and it put the world of astronomy on its heels because it indicated that the universe was accelerating with a mechanism that was completely unknown. And so this accelerating universe was attributed to something called dark energy. And we now know that dark energy would be stronger than dark matter by a factor of 3. The dark matter, in turn, exceeds normal matter by a factor of 5 or 6 or 7 in all places we look. So the universe, if you imagine it to be a driver in a car, is kind of a bad driver. The car has a brake and the car has an accelerator. The dark matter is the brake. So as the universe has evolved, the dark matter acts as a brake on the expansion rate and should have been slowing the expansion rate down. The dark energy is an accelerator and would cause the expansion rate to speed up. In the first part of the history of the universe, the brake dominated. The universe was decelerating. But somehow, in the last few billion years, dark energy and the accelerator have become more important, and so the cosmic expansion is picking up pace. It's accelerating. That's extraordinary. The original observations were made with supernovae, standard candles or standard light bulbs that we use to measure distances to thousands or billions of light years. That method was tested, and actually the two groups that competed in this work both won the Nobel Prize for this discovery of dark energy in the accelerating universe. Since then, it has been confirmed indirectly by other measurements. The diagram at the center shows the convergence between the original dark energy measurement using supernovae, indicated by the blue ovals, that's the error bar on the measurement, and two other methods that we can use to measure the curvature and constituents of the universe. Baryon acoustic oscillations, which is basically large-scale structure in the cluster of galaxies, and the microwave background data in the orange. So the green, the orange, and the blue all intercept a small ellipse, and that small ellipse is the state of our universe. The two axes of these diagram are the vertical axis is the proportion of the universe that's in dark energy, and you see it at about 0.75, 3/4, and the horizontal axis is the proportion of the universe that's made of dark matter, and you can see it at about 0.35, or 1/3 of the universe. So the universe is 2/3 dark energy, 1/3 dark matter, and 3 different methods give concordance or consistency with this estimate. The question, of course, is what is dark energy? In this case, our answer is even more unequivocal than it is for dark matter. We simply don't know. But the observation that led to this discovery of distant supernovae is pretty hard to refute. The Hubble Space Telescope and large ground-based telescopes were used to look at supernovae in distant galaxies. You see the before and after pictures above and below each other for 3 different distant galaxies. These supernovae were used to measure the distance to these far-off galaxies, and their brightness was used to infer the expansion rate of the universe in a Hubble diagram. And that was the first diagram we looked at. So here's the expansion history of the universe again, showing it both into the future and into the past, where we expected a deceleration, the orange region, and in fact we saw a deceleration and then acceleration. The future history of the universe is given to the right side of this diagram, and that's interesting. The universe was already expanding. Now that we know the expansion is accelerating, the likelihood that the universe will reach a maximum size and collapse again is essentially zero. The universe is going to expand forever, and possibly at an ever-increasing rate. We'd love to learn more about dark energy. We actually have very few tools to do this. We're using supernova brightness, we're using lensing methods, and the imprint of large-scale structure of galaxies from the microwave background. These subtle techniques need large and sensitive survey telescopes, and actually we're going to need a new generation of space-based telescopes that haven't yet been funded to learn more about dark energy. Only idea in physics that's on the table for dark energy is the idea that the vacuum of space might be causing this accelerating expansion. We already know that the vacuum of space is able to create particle-antiparticle pairs, number 2 of these diagrams. They very briefly exist and then annihilate with the creation of energy, gamma rays, in panel 3. But is there enough energy in this disruption of space-time from the vacuum to force a global expansion of the universe? It's not clear. And in fact, the calculations in physics are not promising. Because if you do the simple calculation in physics for vacuum energy to explain the accelerating expansion, your answer is off. And it's not off by a little, like a factor of 2 or 3 or 4, or even an order of magnitude. It's off by 120 orders of magnitude. In other words, physics leads you to expect vacuum energy that's enormously stronger than what would be required to accelerate the universe. So it essentially doesn't explain the phenomenon. Now we're left with an even worse problem, where some remarkable and unknown symmetry of nature must have somehow canceled this vacuum energy almost perfectly to allow our universe to come into existence. But how could it do so and leave just one part in 10 to the power 120 remaining? Another thing that's a little awkward for physics to explain is why now? Dark energy and dark matter appear to be completely different entities. We think we know what dark matter is. It's a subatomic fundamental particle that we hope to detect soon. Vacuum energy, we have no hope of understanding it, and we don't know what dark energy is. Yet it seems that they're similar in strength to each other within a factor of 2. And that would only happen one time in the entire prior and future history of the universe. So it becomes a coincidence that we can't yet explain. So, to summarize, dark energy is much more mysterious than dark matter. Its existence rests on unexpectedly faint distant supernovae and a few indirect arguments. Directly detecting dark energy, as we're trying to for dark matter, is exceptionally challenging. So for now, all we can say is that it's a repulsive force that counters gravity. It does not seem to change its strength with time, and so it's actually like a constant that Einstein added to his field equations when he solved them in general relativity, which he called the cosmological constant. Einstein went to Mount Wilson Observatory before Hubble discovered the expansion of the universe and said, "What is the universe doing?" And they said the universe is just static. It's just milling around. It's a big galaxy rotating. Einstein knew that his equations were dynamic and had expanding and contracting solutions, so he suppressed that natural behavior by adding a constant to his solution, which he later called the greatest blunder of his life. In other words, if he'd had the confidence of his equations, he might have predicted the expanding universe that Hubble then found 5 or 6 years later. Physics is giving us no assistance. The vacuum of space does indeed have energy in quantum theory, but it's just nowhere close to the right number. And the density of dark energy and dark matter are roughly equal, for the only time in the history of the universe, forward and backward, that will be the case. Is that a coincidence? And what is it possibly telling us? There are plenty of mysteries left in astrophysics. But before we take our leave of galaxies, let's have one look at the universe of dark matter. Here, a dark matter simulation as we learn to fly in this mysterious universe.
Senses real, fatal attraction is holding me fast. How can I escape its irresistible grasp? Can't keep my eyes from the circling sky. Tongue-tied and twisted, just an earthbound isthmian eye.
And that's the end of this module.